Hello, everyone. Welcome to the lecture on the topic Methods of Join, a fundamental concept in engineering mechanics for analyzing truss structures. My name is Sangeeta Sangma, and today we will learn how to determine the forces acting within each member of a truss using the methods of join. The method of join is the technique used to analyze truss structures. A truss is essentially a framework of beams connected by joints or nodes, and it's widely used in bridges, towers, and buildings. The example of truss in bridge is given in the figure below. The principle behind this method is simple. It's based on static equilibrium. That means at any joint in the truss, the sum of forces must be zero. This is because for a structure to remain stable, it shouldn't be accelerating in any direction. So if we apply the method of joints correctly, we will be able to solve for the internal forces within each member of the truss. The key idea here is that each member in the truss can experience either tension, meaning it's being pulled, or compression, meaning it's being pushed. Our goal is to determine whether each member is in tension or compression and to calculate the exact force in each member. Now that we have an overview, let's go through the steps in solving a truss using the methods of joints. The first step is understanding the truss structure. A truss consists of several straight members or beams connected by joints. The truss is typically subjected to external loads and reactions at supports. The objective is to find the internal forces in each member of the truss. Let me explain you with the diagram I drew. So this straight line are the members. All the straight lines or beams that you can see over here are the members, and the point at which they connect, that is this one, or all the points at which they connect are the nodes or joints. This can also be referred to as the supports. And our objective here is to find the forces acting on each of the members, that is this tree, and also this, and this. The main objective here is to find the forces acting in all those members. The second step is to make some of the assumptions for analysis. Here we assume that the truss members are connected by perfect joints with no friction, meaning they are frictionless, okay? And the second assumption is that the members are treated as two force members. This means that each member only carry axial forces, either tension or compression. The third assumption is that we assume that each joint or all the members are in static equilibrium so that the sum of the forces acting at any joint is zero. These assumptions make our calculations more straightforward by focusing only on the essential forces in each member. The third step is determining the external reaction. So before we start analyzing each joint individually, we need to determine the external reactions at the support. This is essential to keep our truss in equilibrium. To do this, we use three equilibrium equations. The first is that the sum of all the forces in the horizontal direction is equal to zero. That is this one. The second is the sum of forces, all the forces in the vertical direction is zero. And the third one is that the sum of all moments about any point is zero. This equation allows us to solve all for the unknown reaction forces at the support. Now we can head towards analyzing the unknown forces. So we start with a joint that has not more than two unknown forces. This is crucial because each joint analyzes depends on the equilibrium equation, and with only two unknowns, we can solve the equations easily. Typically, this will be a joint where two members meet and where no additional unknown forces are present. The next step is to apply the equilibrium equations at each joint. Once we have chosen our starting joint, the next step is to apply the equilibrium equations at each joint. Once we have chosen our starting joint, we apply the equilibrium equations. That is, the sum of all horizontal forces is equal to 0 and the sum of all vertical forces is equal to 0. Using these two equations, we can solve for the unknown forces in the members connected to that joint. Here's an important point. If we get a positive value, it means the member is in tension and is pulling away from the joint. If the value is negative, then the member is in compression and is pulling away, to pushing towards the joint. Like you can imagine this member, you can just take this member as your reference. Sorry for this. So here, if you consider the force acting is like this, like it's pushing away, so then and your answer for this one came negative in the negative value, like it was after calculating you got minus 20 or anything, then you can simply say that it's in tension. And if you get it in a positive one, sorry, if you get negative, you can say it's in compression. And if you get a positive value like 5 or anything, then you can simply write that this force is in tension. So after solving for the forces at the first joint, we can move to the next joint. We continue this process for each joint in the truss. And as we solve for more forces, the number of unknowns decreases, making each step simpler. The key is to keep applying the equilibrium condition to each joint until we have determined all the forces in the truss member. Once all the forces are calculated, it is time to interpret the result. If a member force is positive, it's in tension, meaning it's pulling away from the joint. If it's negative, then the member is in compression, meaning it's pushing towards the joint. Information is essential for engineers in designing safe and efficient structures because they can identify where the truss members are being pulled or pushed and adjust the design accordingly. Now let us look into some of the numericals. The first question is that a truss of span 5 meter is loaded as shown in the figure. Find the reactions and forces in members of the truss. So we have to find the forces in all the members. I already marked the members as 1, 2, 3, 4, 5, 6, and 7. So we have to find the forces in all the members. Before that, we have to find the reaction. So in order to find the reaction, we have to find the distance AC and CB. So in order to do that, we can see the triangle ABD is right angled at D. So we can, from here we can write that AD is equal to AB cos 60 degree. We already have the distance of AB, that's 5, and cos 60 is half. So the value of AD is 2.5 meter. Now the distance of line of action of the vertical load 10 kilonewton from point A will be AD cos 60 degree. So the value of AD is 2.5, cos 60 is half, so it will be 1.25 meter. From triangle ACD, that is this one, we have AC is equal to AD, that will be equal to 1.5. So once we get the value of AC is 1.25, we can find BC. BC will simply be equal to 5 minus 2.5. So it will be 2.5 meter. AC and BD are both 2.5 meter. And the next, like from triangle CEB, that is this one, CEB, we can write that BE is equal to BC cos 30 degree. The value of BC is 2.5 and cos 30 is root 3 by 2. Now the distance of the line of action of the vertical load 12 kilonewton, that is this one, from point B will be equal to BE cos 30 degree. BE cos 30 degree. The value of BE is BC cos 30 degree. We already wrote the value before, so that is 2.5 into root 3 by 2 and multiplied by cos 30 degree, that's again root 3 by 2. So it will be equal to 2.5 into 3 divided by 4, which is nothing but 1.875 meter. Now we can find the reaction. Before calculating the moment, we'll have to find the distance of the line of action of the load 12 kilonewton from point A, that will be equal to 3.125 meter. And then we'll calculate the moment about point A. Let us remember that at the point at which the moment is taken, the reaction is always 0. So RB, we can write that RB into 5 will be equal to 10, that is the load, and 12 is the load, and 1.25 is the distance, and 3.125 is also the distance. So we can simply write RB is equal to 50 by 5, that is 10 kilonewton, and RA will be nothing but total load minus RB, that is equal to 12 kilonewton. 10 plus 12 is nothing but the total load. Now we'll see or analyze a joint that has only two unknown forces. From the diagram, we could see that there are two joints that have only two unknown forces, that is joint A and B. You can select to solve the either one first, but here I start with joint A. And here we can see that F1 is a inclined force, so we'll resolve into X and Y components. Then we'll solve using the equilibrium reaction. And we know that sum of all the vertical forces is 0. So F1 sine 60 plus 12 is equal to 0. Both are in the same direction, so it will be added up. So from this we can get F1 is minus 13.856 kilonewton, and since it's in negative, we can simply write it's in compression. Next we'll solve for horizontal forces, and F1 cos 60 and F2 are the two horizontal forces, and both are in the same direction, so it will sum up. We already have the value of F1, that is 13.856. So by solving this, we get the value of F2 as 6.928 kilonewton. And since it's positive, we simply write it's in tension. Next, we will draw the FPD of point B. And here, F3 is an inclined force, that is inclined at 30 degree. So we'll resolve it into X and Y components. Then we'll solve using equilibrium reactions. So we'll solve for vertical forces. F3 and RB are the two vertical forces, so and in the same direction. So it will add up, and we get the value of F3 as 20 kilonewton. It's in negative, so we simply write it's in compression. Next, we'll solve for the horizontal forces. F3 cos 30 degree and F4 are the two horizontal forces and on the same direction. So it will add up and we will get the value of F4. That is nothing but 17.32 kilonewton, and it's positive, so we simply write its intention. Next, we'll find for a joint that has only two unknown forces. So the joint C was having the two unknown forces as F5 and F6. There are two more forces, F2 and F4, but we already calculated it. So we can take this joint. And here F6 and F5 are two inclined forces, inclined at 60 degrees. So we'll simply resolve it into X and Y components. And we'll solve for vertical forces. Here F6 and F5 are the only two vertical forces. So we get the relation, by solving this, we get the relation as F6 is minus F5. Then we'll proceed to solve for horizontal forces. Here we see that F2 and F4 are in opposite direction. F5 and F6 are in opposite direction. So the ones in the same direction will be added up, that is this one. And F6 cos 60 degree will add up. And this will be in subtracted from that one. So we can simply write F2 plus F6 cos 60 degree minus F5 cos 60 degree plus F4 equals 0. Or I just change the sides and wrote it directly this way. Then we already have the value of F2 and F4. We will substitute it and find the value. But before that, since F5 and F6 are both are unknown forces, we'll have to find the value of either one. And we already have the relation as F6 equals minus F5. So in this one, we got F6 minus F5 is equal to 20.784. So we'll simply substitute F5 minus F5 as F6. So it will turn to F6 plus F6. So 2 F6 will be equal to 20.784. That is, and then we'll find the value of F6. That's nothing but 10.392 kilonewton, and it's positive, so it's in tension. Then we can write the value of F5 as minus 10.392 kilonewton, and it's in compression from the previous relation. Then we'll find for the FPD of joint E. And here we see that 12 kilonewton is the only inclined force that is inclined at 60 degrees. So we resolve this. We already have the value of F5, but we don't need to do that. We'll just resolve the force along BD because F7 is now the only unknown force that is to be determined, and we can simply solve it this way. So we'll solve for horizontal forces. Here 12 cos 60 degree, F7 and F3 are the horizontal forces. F7 and 12 cos 60 degree are in the same are in opposite directions. Sorry, but there's a bit of calculation error. So F7 and 12 cos 60 are in opposite direction, so it should be in minus, and then will be equal to F3. We can write like that. So F7 will be equal to F3 plus 12 cos 60 degree. Cos 60 is half, so we can write it as 0.5. And then F7 will be equal to F7 will be equal to F3 plus 6. We already got the value of F3 is minus S minus 20. So the value of F7 will be equal to 14 minus 14 kilonewton. And since it's in negative, we can simply write it's in compression. Let us see another numerical. In this numerical, it is asking us to find the forces in all the members of the truss. So in the given figure, we can see that there are some reactions also, but this question can be solved easily without solving all these reactions. So we'll skip the solving of this reaction part. Here is a force that is 25 kilonewton that is inclined at some angle, and we have the distance as 1 1. So using the Pythagoras theorem, we can find the value of this one. That will be equal to root 2. And then if we find the angle, it will be equal to 1 by root 2. That is nothing but cos 45 degree. So the value of theta will be equal to 45 degree. So here we'll solve using equilibrium reactions, sorry. So we have the horizontal forces, that is FEF and 25 cos 45 degree. By solving this, we get the value of FEF, that is 17.677 kilonewton, and it's positive, so we'll write its intention. Then we'll solve for vertical forces, that is FAF and 25 sine 45 degree. It's in opposite direction, so it will be subtracted. We get the value of FAF as 17.677 kilonewton. Then we'll find for another joint that has two unknown forces. FAF, the value of FAF we already got from the previous one. FAB is the unknown force, and FAE is the unknown force, so we can consider with joint A. And here we'll take for vertical forces 45 FAF are and FAE sine 45 degree are the three vertical forces. So by solving this, we get the value of FAE as minus 88.638 kilonewton, and it's in compression. Then we solve for horizontal forces. FAB and FAE cos 45 are the two horizontal forces, and we already got the value of FAE. So we can solve and get the value of FAB as 12.677 kilonewton, and it's in positive, so we can simply write it's in compression. Oh, sorry, it's in tension. Next, we will evaluate for joint E, and here FAE, FBE, FED, and FEF are the four forces, out of which FAE and FEF are the known forces, and FBE and FED are to be calculated. So taking the sum of horizontal vertical forces, we get FBE sine 45 degree and FAE sine 45 degrees equal to 0. We already have the value of FAE, so we can simply write it's 88.638 kilonewton, and it's positive, so it's in tension. Next, we'll solve for horizontal forces. FAE cos 45 degree and FEF are in the same direction, so we can, but it's on the left side, so we'll consider it as negative, and FED and FP cos 45 as positive forces, so it will be subtracted from one another. We already have the value of FPE and FAE, and FED was also known from before, so we can, FEF was also known, so we can solve this and get the value of FEF as 107.676 kilonewton, and it's negative, so we simply write it's in compression. Next, we will evaluate for joint B. Here, FBD and FBC are the two unknown forces and rest are known. So we can solve for vertical forces, that is FB sine 45 degree and FBD sine 45 degree. Minus 20 will be equal to 0. Since these are all acting downwards, we'll consider it to be minus. So after solving this, we get the value of FBD is as 116.606 kilonewton, and it's negative. So we simply write it's in compression. Next, we will solve for horizontal forces. FBA, FBC are in opposite direction, so it will be subtracted. FBC minus FBA plus FBD cos 45 degree minus FBA cos 45 degree will be equal to 0. From this, we'll get the value of FBC as 208.029 kilonewton, and it's positive, so it's in tension. Next, we'll evaluate for joint D, that is the last one, to get the value of force FCD. So we'll just solve the horizontal forces, and here we have FCD cos 45 degree and FPD cos 45 degree, and FDE will be equal to 0. We'll write as FCD cos 45 degree minus FDE minus FPD cos 45 as 0, since these are acting in the opposite directions. And we consider the left side one as negative and right side one as positive. So we'll solve this and get the value of FCD as minus 269.196 kilonewton, and it's negative, so we'll simply write it's in compression. We are done with solving numericals, so now let us look into some of the key points. These are that the method of joint is most effective when there are fewer unknowns at each point. It is not always practical for large or complex trusses with many members, and it will get more complicated, in which case the method of section may be suitable, as you can solve more easily using this method. For large trusses, solution can be aided by software or matrices method. The advantage of method of joints are that it is straightforward and intuitive for small to medium-sized trusses. It can provide step-by-step approach for solving for member forces, and it will also help the engineer to know whether the force is in compression or tension and evaluate the diagram. And the disadvantages are that for large trusses, the method can become cumbersome as the number of unknown increases at each joint, and it may also require many steps to analyze all the joints in large trusses. So, in conclusion, we can say that the method of joint is a fundamental approach in structural engineering. By applying the principle of static equilibrium at each joint, we can determine if each truss member is in tension or compression, as well as calculate the magnitude of force in each member. This method is effective for small and medium-sized trusses, providing a clear path to analyze and design truss structures.